All right, welcome students, happy Monday. Today we are going to be introducing a slightly new topic, right? We're revisiting the concept of acids and bases. We are going to be connecting this topic with equilibrium, with chapter 15, being that now that we have the discussion of reversible reactions, we are going to be able to talk about partial dissociation. We've already introduced this a little bit with the solubility concept, the idea that we can now explain partial solubility with reversible reactions, calculate the solubility using ice tables. We're going to be taking that same type of an approach with acids and bases, and today we are going to be starting with the notion of pH and why it is that we can even measure pH. What does it mean in water? What does it mean to be an acid and a base? So we are jumping back to chapter 16. We're going to be doing chapter 16 straight through from beginning to end, no tricks. So let's get started. The definitions of acid and base that we're going to be sticking with here are the BRONSTED-LOWRY acids and bases. So there are a couple of other definitions like the Arrhenius acid and base, the Lewis acid and base. We're going to be sticking with the BRONSTED-LOWRY acids and bases. And we've already introduced this back in chapter 9, but let's revisit what an acid and a base mean. So an acid is known as an H+ donor in aqueous solution. Aqueous, again, implying that our solvent is H2O. We can look at acids and bases in other solvents. There are other solvent dependencies of acids and bases, but we're going to be focusing with the aqueous condition since this is what we've been focusing on so far. To be an H+ donor in solution then means that we have some type of molecule that has an anion component and an H+ component. This H+ then, when added to water, is going to be able to break off into its own little H+ in aqueous condition, leaving also the anion, this A- in this hypothetical case, also dissolved or dissociated in water. Bases are an H+ acceptor in aqueous solution. So aqueous, again, we're looking at the water environment. An H+ acceptor, what this means is we're looking at something that has some type of lone pair on it. So NH3 is a really good example, or anything that has a nitrogen involved. This nitrogen, if we were to draw out its structure, has a lone pair like so, with a partially negative charge. Now this partially negative charge is able to attract H+ that's floating around in solution. It's going to be attracted to that lone pair. Since this plus charge is a plus, the lone pair has a partially negative charge. In water, then, we are going to end up with a molecule in this example like NH4+, the ammonium ion aqueous condition. To be a Bronsted-Lowry base, then, just means that you're looking at some type of molecule, more than likely with a partially negative charge that can attract this H+ to it. OH- is another really good example. OH-. If we take OH- and combine it with H+, we end up with a classic neutralization, something that's just like water. But the important thing with this OH- is that if we were to draw out the structure of OH-, this oxygen, again, has a bunch of lone pairs, it has a partially negative charge, and this partially negative charge is going to be what attracts our H+. So being able to remember that the structure of our molecules matter, the partial charge of our molecules matter, this is going to help us to determine when we are looking at something that is going to behave like a base. In order to be an acid, in contrast, your molecule needs to have some type of hydrogen that is going to have a plus charge when it separates. So this H+ is going to be the distinguishing feature of our acids. Now, acid-base strength, how likely it is that your hydrogen will leave or how likely it is that your hydrogen will sync up with a base is going to vary depending exactly on that molecular structure. So being able to predict what our molecular structures look like, what the bonding energy is going to be like, this is going to tell us a lot about the nature of our acids and bases. And even before moving forward, we can even just take a pause and ask ourselves, why is it that we care about acids and bases? Like, why are we focusing so much energy on acids and bases? We're looking at a full chapter and a half's worth of content ahead of us. And the reason is that acids and bases play a huge part in the nature of the world around us. Rain that falls and is able to erode rock, the digestive system inside of any type of animal. There's a huge pH influence on the nature of the world around us and the reactivity in the chemical nature of the world around us. So if we can understand the nature of these acids and these bases and how they interact with one another, we're going to get a really good understanding of what is happening in the world around us with just these two key ideas. Okay, so we can predict acid strength in two different ways. We're first going to be looking at what we call the hydrohalic acids, but this is going to be an example of our non-oxoacid case. And oxoacids are going to be acids that have some type of polyatomic ion with oxygen in them, and we'll see how the arguments are going to differ between the non-oxoacid and the oxoacid in a second. So we're going to look at the hydrohalic acids as an example, or an acid that is comprised of H, this is being the hydro piece, and X is the halic piece, or the halogen here. And what we are able to see experimentally is that as we vary the halogen from fluorine down to iodine, down the periodic table, right, fluorine, chlorine, bromine, iodine, we see that the bond strength between the hydrogen and the anion, whatever the halogen is, decreases, right? So the enthalpy, the bond enthalpy between hydrogen and fluorine is very high, versus the bond enthalpy between hydrogen and iodine, conversely, is very low. And we see that there is a steady decrease from fluorine to iodine down this table. So what this tells us about the acidic nature of the molecule is the greater the bond enthalpy we have, so like the HF case, the stronger the bond between the H and the F. What the strong bond between the H and the F means is that the hydrogen is not going to separate easily. It can separate if we put in enough energy, this much energy. We can break the bond if we put in 562.8 kilojoules for every mole of HF we have, but the higher bond enthalpy relative to some other molecules we're looking at, like the HI, means that the acidity of the molecule is going to go down. In other words, HF is a weaker acid, HI is a stronger acid. And we would be able to predict this just by the nature of the partial charge on our fluorine versus our iodine, right? Fluorine is a very electronegative molecule, or electronegative element in the molecule. It's going to be pulling a lot of electron density towards it, which is going to give it a very, very distinct negative charge. It's going to be very partially negative. And this negative is going to be able to hold the H plus more tightly. Not only that, but because the atom itself is smaller, these two atoms are of a more similar size, which means the electrons are going to be more evenly shared across this shorter distance, right? We have a short distance here, short bonding distance. And as we talked back in chapter 6, when we were talking about Lewis structures, the shorter your bonding distance, the stronger the bond. All right, so we have a very strong negative charge on our fluorine. We also have a short bonding distance here. Both of these factors are going to cause the strength between the H and the F to increase, giving us a weaker acid. The hydrogen is going to be less likely to change or separate. The hydrogen iodide, as a contrast to this, we have a hydrogen that still in solution would give us a plus charge. This iodine would still have a minus charge. However, this iodine is super big compared to the H+. This means that the minus charge is going to be very spread out at a very large distance. If this is our nucleus, and this is kind of the size relative to the nucleus of our atom, this very large distance here means that we're going to have a very large bond distance, and we are going to have a weaker bond between the HI as a result. In other words, the distance from this H+ to the iodine nucleus is so great that the hydrogen, this H+, can just leave, and the iodine would not even notice the difference. Okay, so this is how we can describe the hydrohalic acid strength. And this approach, these arguments can be made for other types of non-oxo acids. If we have hydrogen directly bound to some type of atom, like H2S versus H2O, and we were going to predict which one of these two would be the greater acid, we're going to look at the size of the anion here and its partial charge to let us know whether or not the hydrogen is going to be more greatly held or more weakly held. And in this example, we would expect H2S to be the stronger acid, since the sulfur is going to be bigger, its partially negative charge is going to be more spread out. This very large nature, this very large bond distance is going to weaken the bond between the H's and the S, hence the H being able to leave more easily. Okay, so let's compare this to oxoacid strength. An oxoacid is some type of acid. We have an H out in front, but this H is bound to something like a polyatomic ion, sulfate, for example, where we have oxygens present inside of the polyatomic ion. Oxygens present. Now, the nature of the oxygens being here is what causes the nature of this type of acid to differ from the previous, hence why we call them oxoacids. The oxygen is going to matter here. In the table to the right, we have an example of 4 different acids, and the only difference between them, structurally and formulaically, is an addition of oxygen. So our first is HClO, or the hypochlorous acid. Next is HClO2, which is chlorous acid. Next we have HClO3, which is chloric acid. And last we have HClO4, which is perchloric acid. So the additional oxygen going from top down, we can see is going to have a structural effect first on what the acid's going to look like. So here we have in our first, the hypochlorous acid, we have an H, we have an O, and we have a Cl. So this is kind of our color coding. The white is the hydrogen, red is an oxygen, and green is a chlorine. And as we change then the structure going down, we can see that we're placing more and more oxygens on our chlorine. So here we have 2 oxygens on our chlorine, next we have 3 oxygens on our chlorine, and last but not least, we have 4 oxygens on our chlorine. Now what this is going to do is increase the electronegativity away from the OH bond here. So in contrast to what we talked about before, in the hydrohalic acid case, like HF, I said fluorine was more electronegative. This is an electronegativity difference directly between the hydrogen and the species that's bound to it. Here we're looking at a greater electronegativity across the whole molecule. And the electronegativity now across the molecule is going to behave differently than the electronegativity difference directly between the hydrogen and the atom it is bound to. The difference it's going to play is the more oxygens we have present, as we can see here, separating the hydrogen from the oxygen to the chlorine, these blue arrows dictate that we are getting a greater electronegative pull away from this OH. That is going to be the acidic piece of the molecule, right? This OH, this OH, this OH, and this OH are where we have the acidic portion of the molecule. And the additional oxygens on the opposite side or further away from this acidic piece means that we are pulling electron density away from that bond, right? We're not just pulling electron density from the hydrogen to the oxygen directly, we are pulling the electron density all the way across to the other side of the molecule. What this means, or what it's going to result in, is that we're going to have less electron density directly between whatever our X is. In this case, it's going to be our oxygen and our hydrogen, right? We're pulling electron density away from the acidic piece of the molecule, totally away to the other side. This is going to, as a result, weaken the OH bond. If more electron density is being pulled away from the OH bond, there is less electron density to circulate between the hydrogen and the oxygen. The electrons that would be holding these 2 atoms together is now circling away, further away, spending less and less time between the O and the H as we increase the number of oxygens. This is going to result finally in a greater acidity. The perchloric acid, our HClO4, is going to be the strongest acid of all of the molecules that we have illustrated here because we have the greatest pull of electron density away from the hydrogen and the oxygen. All of the electron density being stripped away to the other side of the molecule is going to increase the acidity because we are decreasing the bond between the hydrogen and the oxygen here. The hydrogen is going to very easily drift away in the perchloric acid case. The rest of the table, we have Some additional information, the oxidation number of our chlorine we can see is increasing. The chlorine is becoming more and more positive. Again, as we are increasing the electron density, pulling the electrons away from the chlorine. This last column here, we have this new concept known as Ka. It's not entirely new. This is another equilibrium constant. It's just instead of being a Kc, like directly dependent on concentration, or a Ksp, which dictates solubility product, now we have a Ka. And I'm sure you can imagine what this A stands for. This A is going to stand for acid. So the equilibrium constant here is going to give us a representation of the strength of our acid. How strong is it? We can see that in the first two cases, our Kas are pretty small. We have some number times 10 to the negative 8, and then some number times 10 to the negative 2. And as we increase the acidic strength going up to the chloric and the perchloric, basically what happens here is that we have reached a point where the dissociation between the H plus and the oxygen in the rest of the molecule is so large that we have effectively broken equilibrium. We are no longer looking at reversible reactions. In the lower two cases, we are looking at total dissociation. Chloric and perchloric acids are both strong acids. And because of this, there's no need for any type of reversible reaction representation. There's no need for any type of equilibrium constant. Anytime we're working with strong acids or strong bases, we are going to be able to use our good old stoichiometry to figure out what our limiting reactant is, what our theoretical yield is going to be, and what our excess reactant is going to be. So just because we are moving into a new realm of chemistry, we're looking at more of these exceptional cases, this doesn't mean that you're going to entirely throw all of our old ideas out the window. The idea of a strong acid and a strong base completely dissociating is still true. We don't entirely get rid of these ideas, and as we continue moving through chapter 16 and 17, we will eventually reach a point where we are going to merge these ideas together. Okay, so when it comes to talking about the strength of these acids and these bases, these strong acids versus weak acids, I don't want to get too far ahead of myself. We will be linking strong acids and weak acids and their natures together, but that's down the road. Let's talk about how we actually measure the strength of an acid versus the strength of a base before we start tying all of these concepts together. So the concentration of H plus is measured through the pH scale. So let's define what pH is equal to. So in 1909, the scientist right here by the name of Søren Sørensen defined pH as a way to measure the concentration of H plus. So what he was doing was he was measuring electric potentials or conductivities of solutions as a way to figure out how many ions were present. Specifically, he was looking at this ion right here, the H plus. Now, pH is also useful for measuring the concentration of H plus in bases, because when you are working with a basic solution, there is still going to be a little bit of H plus around. And we will talk about what that means as we link pH and pOH, as we link acids and bases and their natures all together. So what is pH equal to? Well, pH is a logarithmic scale, meaning that as you move around on the scale from the value of a pH of 1 to the value of a pH of 2, what this means is that you have changed the magnitude of your acidity by a factor of 10. We are looking at huge differences here. So the pH is going to be equal to the negative log of your concentration of H+, right? So these brackets, we are using the concentration of notation. The reason why we have a negative sign here is that we are oftentimes working with fractions, and the log of a fraction is going to be a negative number. So just to get rid of the negative, we add another negative, right? The negative of a negative is a positive. So our pH values, if we are working on our pH scale, are going to be positive values. The concentration of H+, if we want to rearrange this equation then and solve for concentration of H+, because that's what this is very useful for, we can measure a pH, or the potential of H+ in solution, and use this equation rearranged to solve for what the concentration of our H+ is. So the concentration of our H+ is going to be equal to 10 raised to the negative pH, right? So we get this just from rearranging the equation from up above. There are some other like P of things, potential of whatever our ion in solution is, pH is probably the most famous. So if you were to have a pH meter, stick it in a solution, and that solution is a pH of, I don't know, 6, we would be able to calculate the concentration of H plus by taking 10 to the -6, slapping on a molar, and now we have a concentration. So this is a very useful tool for us. If we want to know what our H plus concentration of anything in solution is going to be, all we have to do is figure out what its pH is, and that will tell us what our H plus concentration is. And so there is a scale associated with the measurement of pH. This is a scale that I'm sure you've seen before. We tend to talk pretty colloquially about pHs. You know, pH of 7 is neutral, since this is the pH of pure water. If you run lower on the scale, you are working with acids, and if you run higher on the scale, you are working with species that are alkali or basic. And the scale, most classically we can see, goes from 1 to 14. And we're going to be talking actually today about where these limits come from. Why does the pH scale run from 1 to 14? There are species that exist outside of the scale. If we are working with a molecule that has a pH that is less than 1, it is known as a superacid, since it is beyond an acid. For instance, this molecule combination right here, this antimony in the center surrounded by 6 fluorines, is known to be a superacid. It very readily just throws H plus off of it onto other things. Its measured pH is -31. We have very, very much so broken off of the pH scale here. The superbases, in contrast, are above a pH of 14. So the pH of this compound right here is a record 36. The nitrogen present here is able to pull H pluses to it very, very strongly. Now, the reason why or how we get to these very incredible superacids and superbases is because we either synthesize them in solvents that are not water, or they just exist in solvents that are not water. For instance, this superbase, I believe, is a superbase only in organic solvents, things like acetone or benzene, not water. We, however, are going to be focusing on the nature of acids and bases inside of water. So we are going to be focusing mostly on the scale from 1 to 14, but I do want to address the superacids and the superbases in case you come across them either in some type of supplemental video or in some additional reading, or even if it's mentioned in the text. Now you kind of have an idea as to what the superacid and superbase are by definition. So let's focus on water, right? If that's our solvent, what we're going to talk about is how the solvent dictates what our pH scale is going to be. Water, it having a pH of 7, is going to tell us what the rest of our pH scale is going to be, like why our scale runs from 1 to 14, because those are not arbitrary values, they have significance. So let's talk about what that significance is. Water is known to dissociate reversibly, creating H plus and OH minus in solution. Even if there's nothing else present, we have no other ions around, it's just pure water, this water is going to reversibly break apart into H plus and OH minus. This H plus being a species that is very much so of interest to us if we are looking at calculating or measuring pHs. Now, this dissociation does not happen through a decompositional means, right? We don't just have water breaking apart into H plus and OH minus, even though this is the very common form of representing this dissociation reaction, this reversible reaction. What is actually happening, the more technically correct version of the reaction, is listed below. We have 2 water molecules coming into contact with each other, colliding with each other. Now, this collision is what is going to allow the apparent dissociation to happen. We have this partially negative lone pair present on our oxygen here that is going to reach out and grab a hydrogen from another water molecule with a partially positive charge. So we have an attraction here between the partially negative and the partially positive, and according to this hydrogen, its perspective, negative is negative, right? Oxygen is oxygen. There's an oxygen over here on the left and an oxygen over here on the right. So if the 2 waters collide with enough energy, this bond between the hydrogen and its oxygen in the water will break. The hydrogen then will now reform a bond with the oxygen on the right, creating this H3O plus hydronium ion. Hydronium. H plus and H3O plus colloquially are interchangeable. They represent the same species. That's why I have them boxed here. The other remaining species then is going to be our OH minus. The hydrogen now has been lost. We can see that there's an additional lone pair present here, which if we were to draw the Lewis structure just from this formula, OH minus, this is in fact what we would come up with. An oxygen with 3 lone pairs and a hydrogen directly bound to it. This is our hydroxide polyatomic ion. And both of these ions are going to be incredibly important to us, not only for lecture today, but for the rest of this acid-base chapter unit. All right, so if we have this dissociation occurring in solution, or even in just a pure sample of water, we have a measurement available to us. Again, the pH of pure water is 7. This 7 tells us a lot about what is happening in solution, and it defines fundamentally the boundary of our pH scale being 1 to 7. So let's just start with what the pH of 7 is telling us about the nature of the solution, and then we will build ourselves up to the scale being set between 1 and 14. So the equilibrium constant of pure water at 25 degrees Celsius, or room temperature, is something that we are able to find just from knowing that our pH is equal to 7. Since this is a reversible reaction, the simplified version I have here, just the form that's looking at the alleged decomposition of our water into H plus and OH minus, we can write an equilibrium constant, a Kc, representing this decomposition since it is reversible. Right? Any type of math that we want to do with this reaction, whether it be measuring concentrations or, alleged theoretical yields, because this is a reversible reaction, we have to work with an equilibrium constant. It's not enough to use stoichiometry. This reaction is reversible, meaning that we have to use some type of equilibrium constant and equilibrium constant expression. Because the reaction we can see here is a heterogeneous reaction, right? We have water that is in its liquid form, and it is breaking into 2 aqueous pieces. When writing the equilibrium expression, where it's going to be a ratio of products divided by reactants, once again, our only reactant is in a form, right, a liquid phase, that is not something that we ever include in an equilibrium constant. Because the density of H2O is constant, we don't have to include it in any type of equilibrium expression. So the ratio of our products to reactants ends up looking very similar in this case to the KSP examples we just looked at on Friday. When we're looking at solubility of some type of solid, we only ever looked at the products, the ions that were the result of the soluble or mostly insoluble substance being added to water. Here we're looking at something very similar. Water is a liquid, don't have to include it. We're just going to look at the balance of the products that are here. So our Kc, the equilibrium expression for water, is oftentimes notated using this very special K sub W, where W just means that we're looking at water. That's it. Kc of pure water is known as Kw. And the reason why we have this notation for a very special Kw is because everything acid-base related, all of the pHs and the pOHs and the pH scale, it's all defined by water and water's nature. So we are going to gift water this very beautiful and special present that it has its own unique equilibrium expression, its own unique equilibrium constant. Now the equilibrium expression is going to be equal to the multiple of the concentrations for H plus and OH minus. No exponents are necessary since we see that there are just stoichiometric coefficients of 1 in front of the H plus and 1 in front of the OH minus. Okay, so if we want to figure out what this special equilibrium constant is and how it gives us some information on the pH scale, well, we first need to know what the concentration of H plus and OH minus is, right? We need to figure out what this equilibrium constant value is equal to. And as I said, knowing that the pH is equal to 7 is enough to figure it out. All right, so let's see how the pH of 7 is going to come into play. We are working with an equilibrium expression, and if we are set to find equilibrium concentrations from the information given to us, if we set up some type of ice table, we will be able to find these equilibrium concentrations. Now, water, again, is a liquid. Don't have to care about it, just blocking it out. We're only going to be looking at the H plus and the OH minus. Now, if we assume a time equal to 0 before the dissociation has occurred, right before we have any type of product, if we look at the reactant, we see that we only have H2O plus initially before the reaction starts. This means that we have no H plus and no OH minus, since in the wording of the problem, again, nowhere is it listed. Nowhere are we told that we have H plus or OH minus initially. Now, there will be problems where this will change in the future, but for now, again, no H plus, no H minus initially. In order to reach equilibrium, then, this reaction is going to have to shift from reactants to products, giving us some additional X, some change in the product direction. At equilibrium, therefore, that means that we are going to have X amount of H plus and X amount of OH minus in the units of molarity. Okay, this is cool. We now have an equilibrium expression that we can't solve because we don't know the concentrations of H plus or OH minus. Or so it would seem. But again, we have this pH value and we have yet to use it. So let's see where this is going to be useful. pH, whenever we measure a pH measurement is at equilibrium. So the pH equal to 7 is a measurement that is at equilibrium. We have nothing to start with, and so if we were to take this negative log of 0 to give us a measurement for pH, it's nonsense. We don't have anything there. If we wait until we reach equilibrium, well, now we have an H plus concentration where a pH is going to be meaningful to us. So this pH equal to 7 can be used to find what the concentration of H plus is at equilibrium. Now, if our pH is equal to 7, our concentration of H plus that was used to find that is equal to 10 to the negative pH. In other words, the concentration of H plus is going to be equal to 10 to the negative 7 molar. So the pH that is equal to 7 tells us that at equilibrium, once this water has settled into its own inherent nature, reversibly reacting, creating some H plus and OH minus, the H plus concentration is going to be equal to 10 to the negative 7. And as we have seen before in this type of problem, X is equal to X, right? There's nothing special about one X being H plus and the other X being OH minus. So if we now know the concentration of H plus is 10 to the negative 7, this tells us that the concentration of OH minus is also 10 to the negative 7 once we have hit equilibrium. And so these are the values now that we can plug into our Kw, our equilibrium expression for water. Right, 10 to the negative 7 concentration in the units of molarity for H plus, same with OH minus, giving us a 10 to the negative 14. So it's kind of surprising. We have one pH measurement, and that one pH measurement was able to tell us what's the concentration of everything that's in solution, as well as what is the equilibrium expression, what is the balance of H plus and OH minus in solution when our baseline for any type of solution is this water, this solvent that is going to dictate the nature of everything else. In other words, anytime we add an acid or a base to solution, this is the equilibrium that we are fundamentally altering in some way. And so this is how the 10 to the negative 14 equilibrium constant is going to set our pH scale. Explicitly, we're going to see the math in a couple of seconds, like where the 1 and 14 come from. But this is our setup. Anytime we add any acid or base to solution, we are fundamentally altering the concentration of H plus or OH minus in some way. But as we have learned, an equilibrium constant is a constant so long as you are at the same temperature. This 10 to the negative 14 is going to dictate, as we alter pH and pOH, what is the boundary, what is the limit to which we can alter one versus the other, since the two are inherently linked in equilibrium through the solvent being water. Okay, so let's explicitly see where the pH scale then comes from. What does this 10 to the 14 or 10 to the negative 14 explicitly and mathematically tell us? Well, in order to see that, we first need to define pOH, right? If the equilibrium constant, since it is a constant dictating the balance of H plus and OH minus, we've already talked about how to find the concentration of H plus. Let's talk about how to find the concentration of OH minus. Now, the concentration of OH minus in solution is a measure of the alkalinity of solution, which can also be ranked on a logarithmic scale. The pOH then can be found by calculating the negative log of the concentration of our OH minus. In other words, anytime you see this little p here, what this means is negative log of whatever follows after it. So pOH means negative log of OH, and that's exactly what we mathematically see. If we rearrange this equation much in the same way that we did for the pH, we can find a way to calculate the OH minus concentration in solution, and this is equal to 10 to the negative pOH. So the equation looks very similar to the equation to calculate H plus based off of a pH, and that's because the math is set up in the exact same way. The reason why we care about the concentration of OH minus is not just because it is inherently linked to the concentration of H plus in solution, but it's also because bases matter a lot to us, right? Fundamentally, inside of the human body, we have a lot of acidic pieces, but we also have a lot of basic pieces. Saliva can be a little acidic, or it can be a little basic. The brain itself has a pH slightly above neutral. It is slightly basic, and it needs to be this way to be healthy. Your heart and all of the blood that runs through it is also slightly basic. Your liver is basic. All of your pancreatic secretions are basic. All of these pieces are going to be basic. And maintaining a balance between H plus and OH minus is going to be essential for the human body to function correctly. So it's going to be important for us to be able to understand what is the balance of H plus and OH minus so we can further understand the nature of our own bodies and to expand our view, the world around us where acids and bases are interacting all the time. Okay, so let's set up the scale. We now have an equilibrium constant representing the balance of H plus and OH minus in water. We also have a means to represent both the H plus concentration and the OH minus concentration on a logarithmic scale. So let's do that here. Let's shift this equilibrium perspective, this equilibrium expression into something that is more familiar on a logarithmic scale. So we're going to take the negative log of both sides of this equation. The negative log of our Kw is going to be equal to the negative log of the concentration of H plus times the concentration of OH minus. And this may not apparently at this stage seem to be useful to us, but one awesome property of logarithms is that if you have the log of two multiples, like two things being multiplied together, this is equal to the logarithm of the first piece being added to the logarithm of the second piece. So here now we have the negative log of H plus being added to the negative log of OH minus. This is equal to the pH plus the pOH. Now the negative log of Kw is also something we can explicitly solve for since Kw is a constant. So the negative log of Kw is going to be equal to the negative log of 10 to the negative 14. This was the value we just solved for. And here we can explicitly see where the cap of our pH scale comes from. The logarithmic nature of how we measure concentrations of H plus and OH minus is exactly where the 14 comes from. The balance of H plus and OH minus in solution being set to this 10 to the negative 14 is no coincidence. It is how we measure numbers. It is the nature of water itself that we are observing, and the nature of water sets our cap of the pH scale to 14. So if your concentration of H plus is going to be of a certain number, giving us a pH, let's say, equal to 1, the OH minus concentration has to obey our equilibrium constant expression. And how we represent this using pH and pOH is that the remaining concentration here of our OH minus has to sum together with the pH to equal 14. This tells us that our pOH has to be 13. Both of these numbers then also tell us what the concentration of our species is. The concentration of H plus in this hypothetical example will be 10 to the negative 1, and the concentration of our OH minus is going to be 10 to the negative 13. This again balances with our equilibrium constant being 10 to the negative 14. And if all of these numbers, keeping track of all of them, is confusing, well, here I have a chart or a graph, a map that connects all of these pieces that we have talked about so far. The concentration of H plus is going to be oftentimes what we are the most concerned about knowing. If we want to find the concentration of H plus, well, either we're going to have to know what is the pH. This is something that we can measure. And then using the equation of pH is equal to negative log of H plus, we can figure out what the H plus concentration is by rearranging and solving using our pH. However, if we also know something about the basic component of the solution, because our solvent is water, we can use the equilibrium expression for water to also figure out what is our H plus concentration if we know the OH minus piece. Or if we know the H plus piece, we can use that with the Kw for water, right, this equilibrium expression to find the OH piece, since these two concentrations, these two species in solution are inherently linked because of the solvent we are working with. Now we can also find the pOH in much the similar way, the OH minus concentration working with the pOH, but if we know the pH or the pOH, we can use this second form of our expression, our equilibrium expression, to relate these two pieces together. So this flowchart is not anything you specifically have to memorize. Figure out what type of math works best for you, but this will be at your disposal, available to you. In fact, I have attached a PDF or uploaded a PDF to Blackboard that has this chart on it. Not that you can't pause the video right now and write it down, but there is also that PDF that is free and clean and available to you, to download or use whenever you need to. All right, so let's look at an example problem that links these pieces together, the pH and the pOH. What are the values then of the concentration of H plus and the concentration of OH minus in an aqueous solution of NaOH that has a pH of 11.7? So here we are looking at something that is very basic, right? Your pH concentration is more towards the 14 side, meaning that you are working with a base. This makes sense since sodium hydroxide is a very well-known strong base. So there are a couple of different ways you can go about solving for this problem. First, we can use the pH to figure out what the concentration of our H plus is. This is the first and most inherent, direct link that we can see. Right, and the concentration of H plus is equal to 10 to the negative pH, or 10 to the negative 11.7. When calculating this value, this gives us a 2.00 times 10 to the negative 12 molar. We can see that this is a very small concentration. And there are two different ways now we can solve for the OH minus concentration. The most straightforward way would be using our equilibrium expression, which gives us the balance of H plus and OH minus in solution. Our Kw is 10 to the negative 14. The H plus concentration we just solved for was 2.00 times 10 to the negative 12. We're going to multiply this by our unknown concentration of OH minus. Now, if we rearrange and solve for the concentration of our OH minus, this gives us a value that is equal to 5.01 times 10 to the negative 3 molar. And this balance between the H plus and the OH minus that exist in solution, due to the reversible nature of our water being present, now we can see that we have offset the scale. Right, in neutral water, the concentration of H plus and OH minus is equal. Now that we have added some extra OH, the concentration of our OH minus goes up, and the concentration of our H plus goes down. We are functioning on this seesaw here. If one goes up, the other has to go down relative to when we are balanced, the value is equal to 10 to the negative 7 molar equal to 10 to the negative 7 molar. If our concentration of OH minus goes up, which is exactly what we see here, this is greater than 10 to the negative 7, our H plus concentration is going to go down relative to that 10 to the negative 7 value. All right, the other way that we can solve for this problem, or solve for the concentration of OH minus specifically, is since we have a pH, we can find a POH, which is equal to 14 minus our pH, and our POH is going to be equal to 2.3. To solve for the concentration of our OH minus, this is equal to 10 to the negative 2.3, which is exactly equal to 5.01 times 10 to the negative 3. Regardless of the approach that you take, whether you find the POH first, or if you use your equilibrium expression to directly solve for your OH minus concentration, you will find the exact same value. And again, that is because all of the derivatives that we did today, all of the algebra that we did today, is all self-consistent. We used one problem, one mathematic expression, right? pH is equal to negative log of H plus, to define everything else afterwards. So all of this math will always be self-consistently true. If you use two different approaches and you get two different answers, like when you're solving for this OH minus concentration, for example, chances are it's because the math somewhere went wrong. Not that the derivatives themselves are bad, but that either you miss a negative sign, you miss a parenthesis, so always be kind of double checking your work like that. All right, last but not least, it's going to be important for us, since the pH and the POH, or the H plus and OH minus concentrations, are like always going to be in balance. In water, we have to look at all of the sources of H plus and OH minus in order to solve these problems sometimes. This is going to be most emphasized when we're working with dilute solutions. In other words, when we have very few solute particles in solution. For example, if we wanted to look at the pH of a 4.77 times 10 to the negative 8 molar solution of HCl, we would assume, even without doing any type of calculation, our pH should be less than 7, since HCl is an acid. So let's double check this, right? What is the pH when we take the negative log of 4.77 times 10 to the negative 8 molar, since this is apparently the H plus concentration that is coming from our HCl here? Well, if we calculate the pH from this concentration that we're immediately given, it appears as though our pH is going to be 7.32, which is greater than 7, which is going to give us a big old question mark here. How can the pH of an acidic solution be greater than 7? And the answer is, it can't be. We're missing something. And what we're missing is the acknowledgement that not only do we have HCl in solution, we also have water. And as the water breaks apart into the H plus and OH minus components, this H plus from the water directly is also going to have an effect on the pH. So let's learn or look at how to solve for the H plus concentration in a dilute solution when we have such a small amount of solvent that apparently our pH is going to be incorrect. The entire connective thread of this lesson so far has been that anytime we add an acid or a base to water, what we are doing is affecting the balance of the H plus and the OH minus as they dissociate from pure water in its liquid form. All right, so what this means is that if we are looking at the balance now as we have changed some type of condition, what is our new equilibrium condition going to be from the perspective of this water as it is decomposing? All right, so what we have here is a solution of water that was allowed to reach equilibrium and then was disturbed by the addition of some extra HCl. In other words, we are going to add this concentration into our initial component, our initial kind of category here underneath the H plus. And again, just to reemphasize, the reason we're doing this is because we have assumed that water in its pure form had reached equilibrium, and now we are changing the equilibrium. We have disturbed the equilibrium in some way by introducing new initial conditions. This is going to help us out mathematically in the long run. The OH minus concentration, we are assuming that we didn't disturb this initially in any way, right? We didn't add any like NaOH when we were disturbing the equilibrium. We only added HCl. So let's look at how the initial presence of H plus here from the HCl is going to affect the balance of equilibrium. Now we can see that we are still going to have to shift from reactants to products here since we have no OH minus initially based on this like change in conditions. So we're going to get a shift by some amount X towards the product side. So we're going to end up with 4.77 times 10 to the negative 8 plus X for our H plus concentration and X for the OH minus concentration. Now again, this makes sense if our perspective is we have added some H plus, which is what this 4.77 times 10 to the negative 8 represents, and the water is also going to contribute some H plus and OH minus once it has reached a new equilibrium. So the equilibrium values for X can be found by setting up our Kw equal to concentration of H plus and OH minus. The H plus concentration is going to be that 4.77 times 10 to the negative 8 plus X, and the value for OH minus is also going to be X. Okay, so if we want to solve for what the X is going to be equal to here, what we're going to do is rearrange and solve for our X as is presented. So we can set up a 4.77 times 10 to the negative 8 X plus X squared by distributing this X in. And our Kw, which is equal to 10 to the negative 14, we can also pull to the other side, minus 10 to the negative 14. Now using the quadratic formula, we can solve for what X is equal to, and X is going to be equal to 7.90 times 10 to the negative 8 molar. All right, so this change, this difference in our X is going to help tell us exactly what our new concentration of H plus is going to be at equilibrium. We're going to take this X, we're going to add it to the concentration that's the contribution of our HCl, and then we are going to calculate what our new pH is going to be equal to. So taking 4.77 times 10 to the negative 8, adding it to 7.9 times 10 to the negative 8, this is going to give us a new H plus concentration at equilibrium that is equal to 1.27 times 10 to the negative 7 molar. If we want to calculate the pH, which is what we are charged to do, right, we're finding what is the pH. pH is equal to the negative log of 1.27 times 10 to the negative 7, and this is going to give us a pH now that is slightly acidic, 6.90. All right, so I did admittedly speed through some of the math after we have set up our equilibrium expression here. Again, anytime you need to pause these videos to kind of catch a break, absolutely catch that break. I would also encourage you to practice the math down here, solving for our X using those quadratic equations. Make sure that your X value is equal to my X value, because when it comes to taking tests or working through this type of math on your own, I want to make sure that you get that practice under your belt. Again, to emphasize, practice, practice, practice. All right, so we went through a lot today. We went through the entire first, I think even slightly more than third of chapter 16. We talked about the structure and strength of acids, and the same arguments can be applied to bases as well, but the acids are the most straightforward examples. Oftentimes our perspective when looking or studying acids and bases is like from the acid itself. So that was why we emphasized that. We introduced the solvent, our water in this case, dictating a lot of the nature of the acid and base relationship. And that is, again, specifically because water itself is able to break into H plus and OH minus. It has an acidic and a basic component. So anytime you add an acid or a base, you are going to be affecting the nature of water itself. This is going to dictate what your pH and pOH scales balance out to, being that scale of 1 to 14, and all of these strong acids and bases themselves. Though we did not cover explicitly, that information I also attached to Blackboard, uploaded to Blackboard in a PDF as well. It's all in the same PDF. All of these strong acids and bases are available. The reason I didn't go through them in much detail is because we talked about them back in Chapter 9. So I would definitely encourage you to review the Chapter 9 acid-base material to kind of refresh yourself on the nature of acids and bases before we continue and talk about weak acids and weak bases, because we kind of put a pin in that conversation back in Chapter 9, but just like talking about the mostly insoluble compounds, now we are going to take that pin out and have that conversation a little bit more intimately. All right, homework is going to be due on Wednesday then. Homework due Wednesday. Other than that, I have no additional announcements. If you missed last Friday's announcement, the exam that was originally scheduled for this week has been pushed back to next week, so there's nothing coming up for that. Labs will be recommencing this week, but those were both announced last Friday. I have nothing new. So, without anything else, class is dismissed.